Welcome to qnawire.
Here we're asked to draw the molecular orbital diagram of NO, for which we're going to require to generate the diagram, and also we want to find the bond order for this molecule. First of all, the electron configuration for nitrogen and oxygen respectively is going to be 1s2, 2s2, 2p3, while for the case of the oxygen, so for oxygen the configuration is going to be 1s2, 2s2, 2p4. Remember that this is corresponding to the number of electrons that each of one has. So now, in order to generate the diagram, we need to first start with having our energy scale. On the left-hand side, I'm going to write down the atomic orbitals for nitrogen, and on the right-hand side, we're going to write them down for oxygen. So for nitrogen, we're going to have in the 1s, we have 2 electrons. Next up on 2s, we're also going to get 2 electrons. And for 2p, we're going to have 3 electrons. Now for oxygen, the energy levels are going to be slightly shifted. I'm going to write down the energy level for 2p over here. In this case, the relative energy of the orbitals is not really that interesting or necessary for solving this problem, but the atomic orbitals they need to appear over here. Okay. So now that we have this set of atomic orbitals, we're going to generate the corresponding molecular orbitals. I'm going to write them in different colors. And in order to do so, we're going to produce the coupling in between the different pairs of electrons. So over here, the 1s orbital, they're going to interact together and generate different orbitals over here. Same thing happens with 2s orbitals. I'm going to put them here and here. These orbitals are called sigma 1s, sigma star 1s. Next up, we're going to have sigma 2s, sigma star 2s. Remember, whenever you generate the molecular orbital, you're going to have a bonding and an anti-bonding orbital corresponding to that. Next up, we're going to have, for 2p, because of the arrangement for the nitrogen and the oxygen atoms, the p orbitals can produce either sigma interactions like this, or they can produce p-type of interactions as such, or the one that is coming out of your screen that would look something like this. These are p interactions, while this is a sigma interaction. So for the 2p orbitals, we're going to be able to produce, I'm going to put them over here. The lowest one is going to be the sigma 2p set that comes from the p set orbitals for each of the atoms over here. And next, we're going to generate a pair that needs to be degenerate because of the symmetry conditions that corresponds to the pi orbitals. So we're going to have the pi orbitals corresponding to px and py. And as we generated the bonding versions, we're going to produce as well an antibonding one. So we're going to get the pi antibonding and the sigma antibonding. Remember that antibonding orbitals are going to be written down with an asterisk in front of it. So after we have generated the molecular diagram, we just need to fill out the number of electrons. So 7 plus 8, we have 15 electrons. 2, 4, 6, 8, 10, 12, 14, and an extra electron over here, 15. So this is our molecular orbital diagram. Now we only need to generate the bond order, which is equal to the number of bonding orbitals minus the number of antibonding electrons divided by 2. Let's put in a circle the ones that are bonding and the ones that are antibonding. Notice that over here we have 2, 4, and over here we have 6. The ones on the lower bases, they really don't matter. The only ones that we really need to count are the valence electrons, so the ones corresponding to this section over here, because the other ones, they are going to immediately cancel out, because we have 2 bonding and 2 antibonding. I'm going to put the antibonding ones as crosses over here. Okay? So we're going to have a total of 6 bonding electrons minus 1 antibonding electron divided by 2, which gives us a bond order of 2.5. And with that, it would be all. Thank you very much and have a good one.